The Alaska Design Forum presents Skylar Tibbits, founder and co-director of the MIT Self-Assembly Lab, presented with funding support from AIA Alaska and in collaboration with 360 North.
All right, so I'm Skylar Tibbits, and I have two main roles. The first is the editor-in-chief of the 3D Printing Additive Manufacturing Journal, and you'll see how this feeds into all the work that I'm going to show you today out of MIT. But it's an interesting perspective because 3D printing, as probably everyone here has heard of, is a booming field, but more than that, it's something that brings together a lot of different disciplines: designers, material scientists, mechanical engineers, computer scientists, and we really are sitting at this nexus of all of that research. What I'm going to talk most about, though, is the research at MIT. I'm faculty in the Department of Architecture. I run a research lab called the Self-Assembly Lab. We have researchers from all different disciplines, just like the journal. It's very much cross-disciplinary. There's roughly 15 students, undergrads, grads, and full-time researchers from design, biology, material science, mechanical engineering. And all of this started actually from architecture. So I have a background in architecture, and I was interested in how computation, and more specifically code and software, became a new language for design. So there's all these new software tools emerging. This is the very first CAD tool ever invented at MIT in 1953, I believe, by Sutherland, that has its contemporary counterparts in sophisticated computational tools. And these new software tools allow us to design things, to simulate, to iterate, to evaluate our design. So we can create and imagine things that we couldn't have previously done without computation. So code became a new tool, a new language for design, just like the pencil or the T-square or any other new implementation. It allowed us to go further than we could have gone before. And in a similar way, digital fabrication has transformed design. This is the first CNC machine at MIT, the first time they connected a computer with a milling machine. And that has its contemporary counterparts in 3D printing, laser cutters, CNC routers, water jets, industrial robot arms. All of the boom in digital fabrication is doing the same thing that software did. These new tools connected with powerful computation allow us to make things that we couldn't have made. So we can imagine and design things, and we can physically create things that we couldn't have done before. But all of that is more or less nothing new. Everyone here has probably heard about all of that. Our research actually starts after that, where we're trying to bring code to construction. So there's something called mass customization that digital fabrication is often touted as bringing us, that we can produce these mass customized things. But everyone forgets about the assembly problem. This is an installation that we built that had thousands of parts, and your blood, sweat, and tears, wrenching this thing together, and no one wants to talk about that. We show these pretty pictures of these amazing computationally generated and computationally fabricated things, and we kind of skip over the fact that students or many people worked on this for months at a time, brute force assembling this thing. And that was the kind of eye-opening moment where we started to think about how can we bring the sophistication of our software world, that computation brought us, into the physical world. How can we bring that through digital fabrication to materials? And so our research lab specifically looks at materials as an agent, as a way to embed in more and more information. That if we want to build smarter things, yes, we need sophisticated software, yes, we need new digital fabrication tools, but we also need new assembly processes, and the way to do that is to think about materials in a new way. By embedding more information in the materials, we can have the materials making decisions, collaborating with us, giving more agency so they can sense, actuate, potentially assemble themselves. So we look at the materials as the way to bring code to construction. And our lab looks at these human-scale processes, the messy, dirty, human scale world that we all occupy. Construction, manufacturing, product assembly, distribution, the way we interact with our physical environment, our products or our spaces. And we're interested in that realm for two reasons. Number one, because most of the people that are working on the systems that I'm going to show you later in the presentation happen to work at very small scales. There's a boom happening right now at nanoscales, where self-assembly and all of these intelligent capabilities of construction are happening at small scales. And we're looking at how do we do that at big scales. So Feynman famously said that there's a lot of room at the bottom, and he meant that there's a lot of work and a lot of research that we can do at smaller and smaller scales. And most people think that at the human scale, we've kind of done everything. We know how to build cars, we know how to build planes and buildings and shoes and everything you can think of in very complicated ways. So how much is there left to do? And we're arguing there's still a ton we can do. But the other thing that's really interesting to us is that if you look at how we assemble things from all the way to the nanoscale, all the way up to planetary scale, just skip over the human scale for a second. If you think about how our bodies are built, if you think about how plants, animals, any natural system, even any natural non-biological system, think about how mountains are formed, think about how planets are formed. There is no top-down design and no top-down construction. So there's no design of a planet and then a big 3D printer or a big robot that makes a planet. Design, functionality, and construction happen from the bottom up. Everything happens from the interaction of the components. But at the human scale, everything is the opposite. At the human scale, we have genius designers that come up with these brilliant things, and then we tell people or robots to build it. Everything is designed and built from the top down. And we're interested in questioning that, seeing if design, functionality, and assembly can happen from the bottom up. So we study a few different research topics at the lab, and the first one is self-assembly, exactly what I'm talking about. So self-assembly is the fundamental principle that we utilize in constructing humans, in constructing any natural system, or think of traffic jams, weather patterns, movement of people. All of these systems are self-organizing or self-assembling. And the way that that works is you have individual components. Those components come together on their own without humans or robots. So without picking up and placing it, a bunch of parts should be able to build themselves. And that's the fundamental construction technique in most of biology and chemistry and physics. So we look at that at the macro scale. In this case, it's a collaboration with a molecular biologist. You take this glass flask, you shake it hard, and the parts break. You shake it a little bit softer, and the parts come back together. This is in real time forward. It's not reversed or anything. This is pure self-assembly in kind of the most pure way, where you have a number of components that are exactly the same, and they're always going to build this dodecahedron structure, which is modeled after the polio virus, or any virus in capsid, biomolecular structure, self-assembles in a similar way. But what's interesting here is that random energy produces non-random results. Normally, if you think about construction or manufacturing, we have to have more and more skilled labor or better and better machines to get more precise results. So everything is about control. How do we control the process to get better and better results? By having control at every single step. And in this case, we're showing the complete opposite. You can be blindfolded, you can have no skill, no knowledge of the process, and build 100% precise, repetitive things over and over and over again. So a little kid is just as good as an expert because there is no expert. You can pick it up without knowing it. And you give it random energy and you produce repetitive, non-random things. But in this case, it's always going to build the same thing. So in terms of design, that's not necessarily super interesting. Manufacturing, that's exactly what we want. A bunch of parts, build it over and over and over again. In terms of design, we're also interested in how far can we push the limit of design freedom. So in this case, every component is unique. In the previous one, every component was the same. Here, every component has a different geometry and it has different lock and key mechanisms at the nodes. We put them in a tank of water and there's pumps creating turbulence. They tumble around and they only have one place in the global structure. Every part can only find one final position in order to make the chair. So the chair assembles itself with unique components, and the reason we picked the chair is because it's an arbitrary design. It's something that humans have come up with. It's not a symmetric and all-axis dodecahedron structure that can have the self-similar parts. It has to have custom arbitrary parts that have to go together in just the right way to make the chair. So the way that we do that, basically self-assembly has three main ingredients. The geometry is the most important in dictating what's going to happen. So the previous geometry were pentagon structures, then they add up to this dodecahedron structure. In this case, the geometry adds up to a chair. Another project we did was about a self-assembled cell phone. So the components of a cell phone come together. We've done a lot of different ones where you just change the geometry. The second thing, though, is the connections. So in this case, each connection has a lock and key mechanism so that only the right ones connect. So they move around. If it's not correct, then it falls off. If it's correct, it's strong. But the more that assemble, it gets stronger and stronger and stronger. And that's a principle called error correction. Error correction is used all over the place, from digital communication to DNA. In biology, error correction is how we build successful things. So you can do that by patterning the attraction. So let's say you use magnets, you use surface tension, or you use Velcro. You can have positive, negative, positive, or positive, positive, negative, negative. You can create these patterns that ensure that only the right component connects. And then the last one is energy. If you have too much energy, it breaks. If you have not enough energy, nothing happens. You need just the right amount of energy, but it's random energy. It's not guided. It's not that we're placing anything. We're just providing enough energy that they can meet their neighbors and assemble. So in this self-assembly research, we study a bunch of different things. We try to understand the ingredients, like I just talked about. We try to push the limits of design to see, can we have arbitrary and differentiated structures? Can we have repetitive structures? How fast can we assemble? How small can we assemble? In this case, how big can we assemble? So this project is built with 1 meter diameter weather balloons, and at every node is a Velcro node. So in some of the previous examples, there were magnets. You can also use surface tension or other types of connections, but here it's just Velcro, proving that it has nothing to do with the attraction, it's just the stickiness. So they need to move around and just be able to stick when they're correct. And we do positive, negative Velcro. It has a degree of freedom, so it can rotate. And that's because when any two connections come together, they're probably not going to be exactly in the right position. So you allow them to rotate. When 4 connect, it makes a perfect plane. And then when you keep growing, you make these orthogonal lattice structures. So the same way that diamond and graphite are exactly the same fundamental components, but completely different materials just by the structure, we can do the same thing, that the lattice structure grows by those connections and how they come together. So I'll play the video and then talk about it. So that project was really a provocation to think about how do we build things in the future, specifically in extreme environments. So self-assembly, most people will come to us and be like, well, this is really cool, but we're pretty good at building at the human scale. Why do we want to use self-assembly, or when are we going to ever utilize this? And I always point to extreme environments. So think about environments like Alaska, for example, or think about outer space or underwater, or even urban sites where it's really hard to get people. It's hard to get equipment. It's hard to get labor and machines. It's hard to build things. Or think about extreme temperatures, think about extreme scale, super small scale or super large scale. All of those kind of extreme conditions are where we need to rethink how we build things, because our typical process of construction manufacturing doesn't work. It breaks down. Think about how do we build things in the body. Think about different types of surgery, for example. These are scenarios where we need to have new scenarios for construction, and self-assembly is one of those provocations. For example, in this case, we're proposing that you could build structures in the airspace above a site. Maybe you can drop materials from a plane, or you can shoot it, or you can release them from the ground, allow them to assemble in the air. And then as the helium dies, you're left with this much larger space frame structure that assembled. So all of this self-assembly work is what we consider our basic research, meaning we're trying to understand what's possible, we're trying to push the limits, we're trying to understand the ingredients, we're trying to look at it from a design perspective as well as maybe a manufacturing or a future of construction scenario. And all of this manifests itself in art projects, exhibitions, scientific research, papers, grants. You know, the spectrum from basic research to artistic practice is actually much closer than most people think of. And all of this research is really related to those kind of spectrums. It's very speculative. We're trying to see what's possible in the future of fabrication. The research I'm going to talk to you about now, though, is very much applied. We collaborate with a lot of different companies. The vision under this research, it's called Programmable Materials, is to program physical materials to change shape, change property. Essentially what we want to do is make smarter and smarter products, make smarter and smarter materials, smarter environments, but by doing that with less and less and less. We want to take away the motors, take away the electronics, take away the battery and the power and the energy-intensive systems, take away the complexity and the cost. We want to do it with as minimal materials as possible and make them smarter and smarter. So that's the main ambition for the second agenda. And there's three key ingredients here. The first one is the materials. So whenever you're designing a building or a shoe or a piece of clothing or a car, you're going to think about the material properties. So for example, if you start with wood, then we want to think about what kind of activation energy can I use to trigger wood? And the obvious one would be moisture. So if we look at moisture, we know that wood is going to curl with moisture. But you can start the other way. You can say, I have a lot of temperature in my application. So what kind of material can I use that's going to respond to temperature? And you can say metal or thermoplastics, for example, because they're going to likely respond to temperature. So you're trying to link up the material properties and the energy source, but you need to do that in specific geometries. So with wood, it's the grain of the wood. You need to be able to create two-dimensional and three-dimensional geometries that encode some type of mechanical behavior. So folding or curling, twisting, shrinking. We want some useful transformation out of the material triggered only by the environment. So that's the way that we can get smarter materials that do more for us without batteries and motors and sensors, etc. So one of the most clear examples of this is a project that we did in 2013 called 4D printing. So this project, it was a collaboration with Autodesk and Stratasys, and it grew out of robotics, actually. As a grad student at MIT, I was under a DARPA Programmable Matter grant with a faculty called Neil Gershenfeld. And at the time, programmable matter meant if you could just program matter, the smallest of scales or the largest of scales, we could make anything turn to anything else. But the only way we knew how to do that was through robotics. So everyone was making smaller and smaller scale robots or bigger and bigger scale robots because robots meant programming. The problem, though, coming from an architecture background, is that you don't want to make every brick in a building a robot. Because if every brick in a building is a robot, it's going to be super expensive, it's going to fail, and it's going to be hard to assemble. So scalability becomes an issue when you have to build many, many, many things or big things. We really don't want to build like building scale robots that are moving around. They're going to be expensive and clunky and energy intensive. So we started to think about how can we produce materials that have the same functionality as the robots, but we can print them. There's no extra assembly, there's no extra devices and cost, etc. So the way that we did that is we multi-material print. We deposit different materials at the same time through this PolyJet process. The black material is a rigid polymer. It has all the joints, the structure, it's the angles, it's the geometry that I was talking about before. There's another material, it's a little bit harder to see here, but it's called a hydrogel, and it swells based on moisture. So that gives us the material that's going to respond to an activation energy mixed with the geometry, and it's going to transform in predictable ways. The reason we called it 4D printing is because we we wanted to add the element of time. We wanted to basically 3D print things that transform over time. They adapt, they reconfigure, they evolve. That when you produce them, that's just the start of their life. We're not just trying to compete with injection molding or other manufacturing processes, but we want to produce things that have behaviors that we haven't seen before. So that the fourth dimension, meaning time, we want it to transform. It's essentially like printing smart materials, but we can totally customize them. So we can make our own smart materials to transform based on whatever activation energy you want and transform in whatever shape or size you want. Or it's like printing robots, but without all the components. So we print these structures, we dip them underwater, and then a strand transforms into a cube, or a strand transforms into the letters MIT, or a surface that transforms into a truncated octahedron, or a flat sheet that has curved crease origami to make a saddle shape, or a flat sheet that locally expands or contracts to make double curvature, or a 50-foot long strand in a swimming pool that folds into a protein. We made all of these different structures that go from 1D to 2D, 1D to 3D, 2D to 3D. Each one was trying to show a different capability, like folding or curling or stretching or shrinking. In the beginning, we only knew how to make 90-degree angles, so that's why we made cubes, and then we made the letters MIT out of these orthogonal turns. Then we learned how to make any custom angle, that's why we did the protein. Then we showed stretching and shrinking, etc. Each one of these was trying to show that we can encode sensing and actuation with some type of information, that it's going to go from this shape to another shape. But the same question kept coming up. A lot of companies started approaching us saying, can we do this for planes and cars and orthodontics and medical devices and shoes and everything you can think of? But they weren't necessarily interested in 3D printing, and they weren't necessarily interested in plastics. So the vision became much bigger than that. Can we program any material with any industrial process? So we showed that we can do it with sophisticated multi-material printing. Can we do it with lamination and weaving and injecting and any industrial process you can think of? Can we do it with composites and wood and metal and plastic and foam? All of the different materials that we use every day. So that's why we call this programmable materials. And we collaborate with a lot of different people on this, from product designers and mathematicians, computer scientists, material suppliers, software companies, and then a lot of new collaborations on the application side. And we've worked on a number of different materials that I'll show you. One of them is composites, like carbon fiber, Kevlar, fiberglass. Another one is textiles, and we've done a lot of work that I'll show you on textiles, a bunch of different ways to activate them. But I'll start with wood. So wood is an interesting example. As I've already pointed out, there's a lot of examples where we utilize wood as an active material. So you can think about Japanese joinery, for example, where they would use moisture to swell the joints to make them stronger and more precise. Or the Eames example on the left-hand side with molded plywood. They take plywood and mold it into the shape of the chair. Or on the right-hand side, more contemporary example, Akim Mengez's group at the University of Stuttgart uses wood veneer, and the grain of the wood veneer allows the material to open and close based on the moisture in the environment. But this points out two main problems with wood. So in the Eames example, there's a lot of energy that goes into forcing the plywood into shape. So the wood doesn't want to be that chair. These designers came up with this super beautiful chair and then forced the plywood into shape, and that takes a lot of energy. So we're not taking advantage of the material properties of wood. And on the more contemporary example, the wood is opening and closing, so the grain is all of the information. But the problem is that you're limited by the grain you can find. So I think about that as the tree in the forest problem. You don't want to have to go to the forest to find just the right tree that has just the right grain to make your chair. You want to have the behavior of the wood, but you want full design freedom to be able to make your own grain. So the way that we do that is we actually print wood. By printing wood, you can take the behavior of the wood, the cellulose is going to swell with moisture, and we can then create our own grain. We can make any grain that we want. So the way to do that is that we combine sawdust and plastic to make a filament that we can extrude with. You can now actually buy a wood filament to print with. We then print with it an FDM printing process where we make two-dimensional and three-dimensional grains. So we create our own custom grain, we print them out, and then you get them wet. You either submerge them or you change the moisture in the environment, and the different grains will create different behaviors in the wood. So you can get twisting, or you can get rolling, or You can get curling, all different types of angles and curvature. You can get wood that folds to 90 degrees. You can get wood that turns into furniture-like shapes. You can have wood that turns into fish scales. Wood that does things that you would never naturally find, like converging, diverging grains, 2D and 3D structures of wood grain that would never naturally occur. You can even get elephants that fold. So this is the Eames elephant, and we showed that on the left-hand side you can print this fairly complex piece and get it wet, and it transforms into the full structure of the elephant. Or a more clear example, this is with a collaborator, Christoph Gruber, and a product designer, and we printed these flat sheets of wood, trying to emphasize that in 3D printing, typically one of the challenges is time. So if you want to print a big object, it takes a long time because you have to print it layer by layer, and you have to print all these support materials. But if we just think about printing in 2 dimensions, you can print really fast without any extra material. So we print these flat sheets, and then when we get them wet, they turn into these bowls and baskets. And these baskets would be much more complicated or potentially impossible to print with a lot more material and time. So we just print them, we ship them flat, and you can ship them in a vacuum pack seal with moisture, and then when you release it on the other side, it turns into the basket. So another material is composites. We worked with a company called Carbitex who makes fully cured but flexible carbon fiber, and we print or bond or spray or laminate on top. So we take this flexible carbon fiber, we combine it with different polymers. The polymer is going to respond to some activation energy, like moisture we've already shown, temperature, light, so we can change that composition. And then the grain pattern that we print will create the fold or the curl. So we can control the angle or the behavior of the material. So in this case it's twisting, and that's all based on the grain that we're printing, just like the wood, in relationship to the grain of the carbon fiber. So we have control over the behavior, and we have control over the response to the environment by changing the composition of the material. So the left-hand side are simulation, the right-hand side are the physical. And we collaborated with Airbus on an application of this. So Airbus came to us with a challenge. At the top of their engine, there's this hole. And this hole brings in cool air to cool the engine as it's flying. But the problem is it causes drag. So if you have this hole, you're reducing the efficiency of the plane. So if you sit out next to the window and you look out over the engine, there's this hole on the top of all the engines, both Boeing and Airbus. And normally what they would do is they would have this electromechanical flap, or hydraulic or pneumatic flap, the same way that the flaps on the wings are moving. The problem there, though, is that it adds cost, it adds weight, it adds assembly time, and then they have to run control to the cockpit, so it stops production. So we developed a single piece of carbon fiber that can sit within this cavity, and the carbon fiber can open and close, in the beginning based on temperature, and then we move to pressure differential. So pressure differential is like when you're driving down the highway and you roll down the window and everything gets sucked out. That's a pressure differential, because inside and outside have these different pressures, and it creates a force that allows the thing to transform from one state to another state. So just based on wind speed, you can make this valve open and close. There's no actuators, no electronics, no sensors, so it's super light, strong carbon fiber, but it can now open and close on its own. So another material is textiles. There's a lot of different ways to do it. The first way that we started was a pre-stretch. So you take a stretchable textile, like a lycra, you stretch it around a plate, and then we print or bond or stitch on top of it. You can do a bunch of different things. In this case, printing on top of it. You add just a kind of semi-rigid polymer or some semi-rigid layer. It could be a stitch, for example. And the geometry that you create on that textile encodes the information of how it's going to transform. So a circle, for example, when I cut it out, is going to then jump into a Pringle shape or a hyperbolic paraboloid. So because of that pre-stretch, it's like a jack-in-the-box. It's going to jump, and the geometry that you print is going to tell it what to turn into. You can create pleating and tufting and all sorts of different complex geometries from the textile just by stretching it and printing. Again, with Christoph, we did a project at the London Design Museum where we took a sheet of textile and we printed this fairly complex pattern. When you cut it out, it then transforms into a shoe. And the exhibition was on the future of shoes. And our take on that was to think about manufacturing. So if you look at the manufacturing of shoes today, it's tens or hundreds of components that are almost always manually assembled. So they're stretched, they're formed, they're stitched, they're glued, assembled together into this super complex shape. And we have all these different sizes. There's a lot of energy that goes into the shoe production. So we were showing that with just a single material, stretched and then printed on, you can then make the full shoe, the uppers and the outsoles, all the curvature of the shoe. Another way to do this is to combine what we showed in the composites with textiles. So we started to make our own fibers and filaments that we could knit or weave to create these sort of macro scale textiles. And these textiles can then be activated by temperature or light. In this case, it's an IR light, or it also works with sunlight. And it's roughly 30 to 40 C, so nearly body temperature. And they can transform in what's called an auxetic way. So normally with materials, when you stretch them, they shrink in the other dimension, or when you push on them, they bulge. In this case, auxetic materials expand and contract uniformly. So when you stretch it, it also stretches in the other dimension, which is really unique. And the reason that that's interesting is because if we can control the expansion and contraction, we can control the behavior for like breathability in clothing, for example. You can control how materials expand and contract with body temperature, or packaging, or crash protection. You can control how much a material expands or contracts in 2D or 3D. And we can do that with temperature, moisture, or light. Another way to activate textiles is by changing the structure. So this is what's called a biaxial braid. Biaxial braid is like a Chinese finger trap. And what's interesting about that is the flexibility and the structure is completely by the material braid. So there's no connectors, there's no joints, it's just over, under, and that creates stiffness and flexibility. So you can puppeteer these structures and make fairly large-scale things. This is a 30-foot tower that we're here load testing to measure the deflection of it. Again, it's just over, under. And then we made a 60-foot version. So this is a much larger version. There's a small person, or a normal-sized person, or a big tower. And that person, a single person, can transform the tower. This started as a collaboration with two companies, Atelier One, which is an engineering company, and Tate Towers, and they make rock shows, so like Adele or U2 or Olympic performances or Cirque du Soleil. They work on these transforming things. They're like architectural scale robots often, and they're super expensive and they're complicated, and they have all these actuators, hydraulics, pneumatics, electromechanical systems. And they're interested in finding ways that we can have architectural scale systems that transform the same way that textiles can transform, the same way that a sweater, for example, or the Chinese finger trap so fluidly morphs with very minimal forces. So we built this much larger scale version and then started a collaboration with Google, and we looked at the office spaces. So in offices, you have fixed offices, like closed offices, that are great for privacy, but terrible for flexibility. And then you have open offices that are terrible for privacy, but they're great for flexibility. So we were proposing that you could have transformable spaces, like a meeting space that can transform, come down from the ceiling when you need it, create a private room, or you can have walls or pods or phone booths. You can have all of these interior spaces that transform, that expand and contract with very minimal forces, exactly like a textile, but on an architectural scale. So these are just some of the configurations of that one. That one's made out of walnut veneer on the exterior, and then the biaxial braid with fiberglass composite on the interior. And then one other example of a morphable structure at large scales. This is a student project. Undergrad students with roughly tens or low hundreds of dollars made a 30-foot tower. This is all made out of weather balloons, and then there's a textile around it with 3 tendons. And just by pulling on those tendons in just the right combination, like A, B, A, C, B, A, you can create any 3D structure, like a helix, for example. You can make this single tower morph into any shape. So basically a 30-foot robot for tens or low hundreds of dollars that you can assemble in less than an hour. So we're really interested in these systems of transformation, both from very small scales to very large scales, from moisture to temperature to sunlight to physical forces, all about things that physically transform in programmable ways. So the first research topic was about assembly. The second one was about programming transformation. And this third one is about phase change. So how do we go from solid to liquid, or from stiff to flexible? So not necessarily about shape change, but the phase or the property of the material. So one of the principles that we look at is called granular jamming. So granular jamming is when you go to the grocery store and you buy coffee and it comes in this brick and it's super stiff. That's because the granules are jammed, they're stuck. There's nowhere for them to go, and by being stuck, they are solid. But when you cut it open and you pour it out, it flows like a liquid. Or when you're at the beach and you jump on the sand, it's hard, it's really stiff. But when you play with it, it's really soft. And that's an interesting phenomenon because structurally on the right-hand side, that's a liquid, but we know it physically as a solid. And you can reversibly go back and forth between solid to liquid, liquid to solid instantly. So we've done a bunch of projects, one on acoustic tiles that can adapt from different textures, and then another one on reversible packaging. So with Steelcase, a furniture company, we did a project where they normally take their furniture, their chairs, and ship them from factory to factory, and they wrap blankets around them. But in our case, we developed this blanket that has foam beads inside of it. You pull a vacuum on it and it jams around the chair and it turns into styrofoam because all the beads are foam. And then you ship it, and on the other side you can release it and wrap it around a different product. So you don't have the styrofoam that you then have to destroy or have all this complex tooling. You can just reversibly have packaging that'll protect the product. But you could also fill it with coffee or grass seed or any type of granular material and then have all of that when you ship it to the customer. But more interesting than that is a project that we did with Gramáció Koller at ETH. We were interested in trying to find a way to use granular jamming for architecture and construction. And there's two main problems. The first is the membrane and the second is the vacuum. So you don't want your building to be constantly requiring a vacuum because that's going to be super energy intensive. And you don't want it to be super susceptible to puncturing. So you don't really want a membrane. So we found a way that just by combining rocks and string, literally loose rocks and loose string, there's no extra components, you can promote jamming. So in Chicago for the architecture biennial in 2015, we did this project where you have this yellow bounding box and we layer rocks and string, rocks and string, rocks and string over and over and over again. And the robot is printing out the string in very specific patterns. It's just laying string layer by layer on the rocks. And when you release the bounding box, all the rocks that don't have string fall away. And only the rocks with the string jam. And the reason that they jam is because the string takes tension, the rocks take compression, and there's nowhere for them to go. So the rocks want to fall away and they want to fall into an angle of repose. So every material, every granular material has a different angle of repose. They want to fall to that, which is what you see at the bottom. But because of the string, they have nowhere to go. The string is taking tension. And this tower can hold 3 tons before it collapses. So you can make a super load-bearing structure. But what was interesting to us about this is the instant nature and the reversible nature. So if you think about construction today, we typically would use concrete, for example. Concrete is great because it comes as a liquid and turns to a solid, but the problem is it takes forever. So one of the leading costs and time in construction is just waiting for concrete to cure. And in this case, it's a liquid. We pour it as a liquid, like we talked about before, but it's instantly solid. There's no waiting for it to cure. And it's 100% reversible. So if we, at the end of the exhibition, we just have this spool, and if we wind up the string, then the whole tower disintegrates. And you're left with exactly what you started with, a pile of rocks and a spool of string. So you have exactly the same materials. There's no waste. We started with a pile of rocks and a spool of string, and now we have a pile of rocks and a spool of string. We can move it, instantly cure it, make a solid structure, reverse it, move it, make a solid structure again. So it's basically a reversible concrete process. And we've done a lot of different research on that. We're now doing sand and coconut husks, because sand, you can shoot it. So you can vacuum it up and shoot it, which allows you to pour it much easier than shoveling rocks. And with fibers, like coconut husks, for example, they're natural, but you can also chop them up and shoot them. You can spray it, so you can go even faster. I'll show one last project that's also on phase change, but in this case, it's a new printing process. It's the most recent project. Just in December, we did the latest exhibition on this. It's called Rapid Liquid Printing. This grew out of another collaboration with Steelcase, and they were interested in 3D printing, but had some of those challenges in mind that I've been talking about. Specifically, there's 3 challenges in 3D printing: the size, the speed, and the material properties. So 3D printing is just too slow, it's too small, and the material properties are really poor. So we came up with a new process where you print into gels. And by printing into a gel, you eliminate gravity. So without gravity, you can print in 3D space, like calligraphy. So you're just drawing in 3D space as fast as the machine can go. And by changing the pressure of the extrusion, you change the thickness. So exactly like calligraphy. The material then cures underneath the gel, so you don't have to wait for it to cure. And you pull it out and just wash it with water. So this is much, much faster because normally in 3D printing, you have to go layer by layer. And in our case, there is no layers. You just draw in 3D. But you also don't have to print support materials. Like normally in 3D printing, if you wanted to print that shape, you'd have to print all the support material so it doesn't collapse with gravity. In our case, the gel is the support material. And then we don't have to wait for it to cure. Like in FDM printing or SLS printing, you have to cure the material at every single step. We just draw the whole thing and then it cures all as one. So we can print small things like millimeter scale things. We printed a hammock, so a 10-foot long structure. You can print big things, small things. But maybe most interesting is the materials. So this is a beach bag that we printed for Design Miami, made out of silicone. So silicone is interesting because almost no other 3D printing process can print with silicone, but we can print with a wide range of materials, all industrially off-the-shelf materials. So no strange, our own complicated mix of materials. These are just readily available, readily well-known, well-characterized materials like any silicone, polyurethane foam, plastic, rubber, any acrylics, resins. We've tried concretes, low-temperature metals, a lot of different materials that have properties like that, this jiggly silicone rubber bag that you could almost, it'd be almost impossible to print with any other process. And we print the entire bag as one piece. So this was exhibited in Miami.
We lost our video feed.
Oh, yeah?
Sorry. The bag was about to be shown.
Sorry. Let's see, let's try it again. There we go. So we exhibited this in Miami, and you can see what we're interested in here is the kind of design details, the calligraphy of it, where the design of the structure comes from the printing process. And it's not like we're trying to just take an existing thing and print it in a new way, but we're trying to invent kind of a new design language. And we exhibit it by showing the actual printing process of the bag in the gel. So each bag was printed there. It takes 45 minutes to print one bag. It's definitely not an optimized process, so we could probably go faster. But in our case, this printing is minutes to hours. And in normal printing, it would be impossible, likely, to print that. But even if you could, it would be hours to many days. So it's dramatically reducing the time for printing. So where is all this crazy stuff going? The first thing to start out with is that we're a research lab, so we're kind of able to hide behind that and say that we're exploring and we're trying to push the limits of what's possible. We have basic research like the self-assembly work, and we're trying to see how far can we push it, what can we do from a design and art perspective, what can we understand from a science perspective. And then we have applied research like a lot of the programmable materials and the phase change research, where we're trying to collaborate with companies and push the limits of behaviors and materials, create new products that have new behaviors that we haven't seen before. But this image to me is indicative of the problem that today's manufacturing construction is based on this. This is sort of the state of the art, that we have super complex things that come together in complex ways with tons and tons of parts, lots of man hours, trying to make more and more complex things. We're always trying to make better, more sophisticated things. And basically there's only two solutions that anyone talks about. The first one is cheaper labor, but that's not going to happen probably. The second one is what everyone's putting their money on, which is more and more automation. Everyone thinks that if we just have more and more and better robots that are somehow cheaper and more precise and better than humans in every possible way, it's going to solve all of construction and manufacturing. And we have two different perspectives on that. One of those is, let's just assume that's true. Let's assume that automation is going to take over and it's going to solve all of our problems in construction and manufacturing. Even if that's true, we should still have better materials. We should still be making things with smarter and smarter materials, because those materials can collaborate with robots. The robot maybe could be really bad. It could just place the part generally in the right region, and then the part could assemble itself or could become more precise so the robot doesn't have to do everything. Or maybe the part is going to sense forces or make decisions locally and inform the robot of what to do next. Or maybe we just assemble the same way we normally do. Maybe we're just going to assemble in a typical fashion just with robots, but the products that we make should be smarter and smarter. So we should make smarter clothing and shoes and cars and buildings that are responding to the environment, responding to humans, adapting without electromechanical complex devices and power requirements. We can still make smarter products, even if automation is the solution. But we're betting on a second scenario, which is more ambitious. But what we're showing, and many other researchers, is that materials are robots. So all of the DARPA research that I was talking about before, if you look at all the researchers that were under that research grant 10 years ago, almost every single one of them is working on soft, squishy, gooey material things. Almost none of them are working on electromechanical robots anymore. And that, in my mind, is showing a shift, that materials, I believe, are the future of robots. Materials show sensing, actuation, and logic, which are the fundamental ingredients of robotics. But more than that, we think that this offers a new perspective on the product life cycle. And that starts with materials, obviously. What we're specifically proposing is that it's not about inventing some really complex, crazy, radical new material. It's about taking all the materials that we have today, like textiles and metal and foam and rubber and plastics, all the things we already use, but giving them all these new properties by using digital fabrication processes or thinking about what can the material do, how can it respond to the environment. And that allows us to think about new types of assembly where the materials assemble themselves or they collaborate with us in new ways to build products. It allows us to think about shipping, packaging, logistics in a new way. Perhaps the package could assemble itself. Perhaps you ship the product, it transforms on the other side. Maybe we could build packages that adapt to the environment, keep the product safer, control the climate, for example. It allows us to think about new products. Maybe we can have the same exact products with new behaviors. So all of the clothing and shoes and cars and planes that we already have, they can be exactly the same, but now they can be smarter and they can respond to us and they can control our climate, they can adapt to the sun, et cetera. Or maybe there's entirely new categories of products that we haven't even thought about before because we have these material properties that we didn't have. But maybe most important is the reversibility and recyclability. So if you have self-assembly, you sort of get self-disassembly for free. So you can have something transform, you can then reverse it back to its constituent parts, like the rocks, for example, and have the fundamental components you can build back up. Or you can have a product that adapts and gets better over time, or becomes a different product when you need it. Instead of throwing it out, it adapts to become a different or better product. So we believe today we program computers and machines, and tomorrow we'll program matter itself. Thanks so much. Q&A?
Yeah.
Questions?
Questions?
So did
Thoughts?
Zaha Hadid, the architect, use a lot of that stuff for her curvy buildings?
Actually, I worked with Zaha, so that's an interesting connection. So no, any of the contemporary architects today are not using what I'm showing you, but everything I'm showing you came out of that. And I was a student in undergrad studying when Gary and Greg Lynn and Zaha and Tom Main and like all of those architects were booming, and software was the only way that would allow them to build those buildings. So they had sophisticated software tools and their own programs that they were writing in order to calculate how to produce this panel. But they would produce this complex panel, and every single panel was unique. You'd have like, tens of thousands or hundreds of thousands of panels, every one being unique, and now you have a massive puzzle. And you have to figure out this panel has to go with some other panel somewhere and come together in a really complex way. So they were able to make these complex things through sophisticated software and fabrication, but it was brute force construction, assembly, labor. And so my generation, I think, is critiquing that, saying like, beautiful software, great, design, amazing, fabrication, unbelievable, they pushed the limits, but construction was really poor. It's really brute force. It's much worse than just building a straight up bad building, because it's much easier to build that. It's much less expensive. It's much better to just build that. And that's not really where we want to go. So we need to think about the construction side of it. And that's what really started all this research was that. Yeah.
So on self-assemble, items that self-assemble, it seems to me that unless the way to get to the target geometry that you're aiming for, that there's likely to be other local minima so do you spend a lot of time programming or thinking around the problem of getting the wrong structure?
Yeah, totally. And the way we think about this in terms of like entropy, for example, is what's the most comfortable state it can fall into that is a useful state for us. And we're always trying to think about like, how does it just naturally want to fall into that state? But we've done a bunch of other projects. One of them, for example, was like, you have a big flask, you throw yellow and black parts in there, and through chirality, or right-handedness and left-handedness, we can ensure that always the black assembles and the yellow assembles, and you never give a soccer ball of black and yellow. And that's one way to design the geometry. Another one that we did was you had a tank, you throw a bunch of parts in, and there's a catalyst, and only by changing one part in the entire system can you make it turn into a cube or a chair, for example. So you just change the one part and you can guide it to go this way or that way. You can change the environment, like by having more of a kind of true catalyst, like a bowl, and you can promote certain things. But we're always thinking about that. How do we make sure that it's actually not going to do something else? And maybe more interesting than that is like, we're excited about the design prospect of not having top-down design with bottom-up construction. Like a lot of the things I've shown here is like predetermined chair or predetermined MIT or whatever shape, and then having it self-assemble or self-transform into that. But we have a bunch of other projects looking at maybe based on the local environment, it could decide one way or another to go. And there could be like sort of logic modules. And by combining these logic modules, you have like a massive amount of design possibility. Everything is in some ways predetermined, but it's all based on the combinatorics and the environment, the relationship in the environment. You get different designs. And I'm really interested in that. The challenge there, though, you have the spectrum from like totally predetermined to total pile of junk that no one understands, to something in the middle where it's like recognizable or useful or functional, but design is still open. You know what I mean? And that middle space is like the really beautiful one. We're mostly showing that we can build things that we've predetermined, and that shows you that it worked. But if you shift more towards like letting the design emerge, it's even more interesting. Yeah, because then we could imagine structures that would be way higher performing, better design. Like I throw a bunch of parts in and I want the design of the chair to emerge, not me tell it what to look like. You know what I mean? So do you know software of topology optimization? Yeah. So that physical, like you have a box, you subject it to forces, and the design of the chair emerges. That is like the optimal structure of those forces, or whatever the function criteria is. That's where we want to go. Yeah. Yep.
So it seems to me that living organisms are like the ultimate self-assembling things, and we're now programming organisms to make stuff for us. So it seems, is there going to be a place in the near future where you're going to harness life, either through recombinant genetic engineering kind of stuff, in order to make the materials that you're using?
It probably won't be us, but some people, definitely. There's a bunch of programs. One was called the Molecular Foundry program, and the other one is called the Atoms to Products program. They're, I forget which agencies were running them, and it's exactly that. Like, can we make molecular factories to make anything that we want using self-assembly? And SymBio, basically like genetically programming them to be factories to produce other things. Our work tends to be, we've done a couple things based on biological materials and a couple collaborations, but we tend to kind of have a more like, let's say like human scale perspective on it, that we try to work with everyday materials like woods and plastics and foam and whatever it is, not necessarily biological materials or like new material science, because there's tons of experts that are doing incredible stuff. Everything I've shown you is like totally obvious in biology and nanotechnology. Like that's the only way that they can build. And there's a group called, or a group led by Peng Yang at Harvard's Wyss Institute doing DNA origami. So you can take the ACTGs, you can make like any custom like AAA, CCC, whatever, get it in a test tube, and then combine it, heat it and cool it and cycle, and it'll make like any letter of the alphabet, any 3D shape, like spaceships and like nanoscale with DNA. Incredible work. That's basically the 4D printing thing I showed you, but like with DNA, and way more complex and sophisticated. And there's a lot of people in SynBio and material science that are doing a lot of that work. So we tend to be at the human scale trying to think about like just everyday materials. And I think that gives us a leg up towards application, because these are well-known materials that we've been using for centuries. And we can now give them new behaviors just by kind of listening to them and fabricating and collaborating with them to kind of tap into their properties. So that's the kind of angle we take. I'm sure that there will be much more happening in the SynBio material science realm in the next decade, and that's like booming right now. But yeah, we're taking kind of the same fundamental principles but applying it to everyday materials. Yeah.
So do you think the two approaches could come together
totally
in the next 15 years
it's
or
the
so?
same vision, definitely. And material science is not, not all of material science is obviously looking at biomaterials. There's a lot of, synthetic materials that are being developed, and some of them, by the way, one kind of sidetrack thing that I'm interested in and a little bit scared of is like the obsession with biomimetics, because it becomes a sort of dogma where everyone thinks that like if it's biology then it's good. But there's all these amazing things like we were talking about today, all the like think about like rocks and metals and all these like non-biological but natural things that are also fascinating. And so what we're trying to do is like, what is the fundamental principle underneath the biology, underneath chemistry, underneath physics of why these things assemble? It's not about biology or chemistry. I mean, that spectrum is very blurry of when it goes from one to the other. And we're interested in the principles, and then we can translate it to fabrication and geometry and all these things. But it's exactly the same ambition, goal. It's like information in materials, and that's what we're all doing. And we have like different realms, and at some point there will be blending of synthetic and living, and they're all going to be blending. But our main expertise is, I would say, not in the biological realm, so we tend to not work with biomaterials, but there's definitely other groups doing that. Yeah. Yep.
You've been watching a presentation of the Alaska Design Forum, presented with funding support from AIA Alaska and in collaboration with 360 North. This program was recorded March 28, 2018 at 360 in Juneau.